Hey, what's going on, guys? Z here. In this video we're gonna code a matrix screensaver in x86 machine codes. So the way to go is the following. I'm gonna input the line of assembly code, then talk through it, like what it does in particular, why do we need that line of code, and then I'm gonna be making some hand assembly, which means turning this line of assembly into the machine codes, and there will be a few within a single chunk, and we'll have up to 3 chunks. So we'll then take that chunk of bytes of machine codes, enter this into the hex editor, run, see the output, and then go for another chunk and then for another, and that's the way to complete the entire program. Okay, and now just a few words about the development environment I'm currently working in, and how you can reproduce the steps seen in this tutorial on your site. So I'm developing under the GameOS, which is the operating system I've developed for creating boot sector games and apps. It's the 16-bit real mode operating system, just like MS-DOS, but much more simplified. It's really minimalist. And you can run it in the online emulator. All you need to do that is just to download the gameos.img file, so the image file of the operating system, and that's the bootable one. Well, if you want, you can write this on the USB flash drive and try it on the real hardware like I do, but that's not necessarily needed at all. So at the very end, we'll see, by the way, how this matrix screensaver that we're going to be writing is going to look like, how it's going to run on the real hardware, just because that's really cool. That looks really cool, almost like in the Matrix movie. And yeah, this is pretty much all about it from my side in regards to the intro. So let's have a look at how the end result of what we're supposed to be developing is going to look like, and then we'll jump in straightly into the development. So if I just say prog2, and here is the output. So this is how our matrix screensaver is going to look like. So it would be outputting only the digits. Okay, and it's quite pretty simple, but it's challenging enough for it's challenging enough, bear in mind that we're going to be writing this in machine codes. Okay, so we're going to be storing our screensaver as prog1, and now just to give you an idea what are the progs under the GameOS, what this means. So we just type help. Here we have 5 user-defined programs, and the prog2, which I've just demonstrated, already contains a matrix screensaver. And the rest are just the placeholders. So if I just, let's say I type prog1, I have a placeholder code which is compiled along with which is assembled along with the operating system. The entire operating system is written in assembly, so yeah, it's better to say assembled rather than compiled. Okay, so in order to run this into the hex editor, so hex editor looks like this. Okay, we can just enter the address and then the bytes, right? And it starts from the address 00000500 hexadecimal, and in order to load whatever we're going to be working with here, all I need to say is just load and then the prog that I want to load, so prog1 edit, and here is the code for those messages that you've seen, like this is the prog1 placeholder and so on. So we need to erase this now, so I can say new and go back to edit, so nothing there. Now if I just say save and prog1 again, and now let's reboot to make sure we start from scratch. So edit and nothing there. Okay, and if I now try to run the prog1, nothing appears because it's currently empty. So if I just load prog1 and go to edit, we have nothing there. So I've just erased the prog1. So I hope this is clear. Okay, so now we're going to be hand assembling the code, putting this into the hex editor, and before we run the code, just because if there is something wrong, we'll need to retype this from scratch every time. So I prefer to save that before running the code. So we'll save that and run as a prog1, and that's pretty much all about it. Okay, guys, so now let's go to the tables. So here I have a table for ASCII characters. But I already kind of like remember by heart those characters that we need to work with. But if you don't know what's the hexadecimal value for a given ASCII character, you can reference it just here in this table. Also, it contains some useful interrupts, useful BIOS interrupts, which we're going to be relying on. For instance, we're going to be setting up the 80 by 25 text mode. We're going to be hiding cursor as well. So we're going to be relying on this information being presented in this table, right? So this is just the reference of where we can take that, okay? And another table which is absolutely essential is the table of opcodes. So this is the information that is needed in order to translate x86 assembly into x86 machine codes. So I hope that's clear. Okay guys, so now without further ado, let's jump straight into coding. So the very first thing I want to do is to initialize, like clear the screen completely. So initialize the 80 by 25 characters text mode. So I need to put the value of 00 to register AH, and the high 8-bit register from of the AX 16-bit register, and 03 hexadecimal to the lower to AL. But doing this in 2 commands takes just too much, so we can do this in 1 run. And all I need to do is just say move to AX. I want to move the 0x0003, which is so first 00 is like for setting the video mode, the BIOS code to set the video mode, and 03 is the video mode that we want to set. This is the text mode, 80 by 25. So if you don't understand where it comes from, just drop back to the ASCII table and you'll see this initialization codes there. Okay, so now we need to turn this into machine code. So we have lines from 1 to 9. Here are 2 tables, and what we need to do is to put the immediate data into the register. This is the line 1, and first I would be typing the kind of like formatting formula or a placeholder, right? And then in the next run we're going to be just assembling this. So first we have B is hexadecimal, then W is the placeholder, is a placeholder bit, so it would be 1 in case of 16-bit registers and 0 in case of 8-bit registers. So I just say this once, and then I'm not going to be talking about this again because this video takes ages otherwise, right? And then the format goes, so we need to specify the register we want to put the data to. So in this case, this is AX, and the value of AX, you see like the top left corner of the screen, is 000, right? And then the value that we need to input here, so I would have say like 0003, but x86 architecture is little endian, so it uses the little endian byte order. So this means that I need to swap the bytes like from back to forth. So this would be 0300, all right? And I'll drop this line as is for now, and I will type a few more lines, and then we'll go for assembling, and then at the end we'll extract the machine codes. It's just the most, for me personally, currently it's the most convenient way of developing. Okay, so the next thing to consider, we need to call the BIOS interrupt 10. So I can say just simply int hexadecimal 10, and this is needed to actually to fire the BIOS interrupt to actually set up this video mode that we've just initialized the parameters for. So I'm using the lookup. So in the right part of the screen, I'm sorry I don't have a mouse pointer here. So in the right part of the screen there is the int directive. So we have int. Int is turned to CD hexadecimal, and then just the address. So we have not the address, then the constant, sorry, and we have the constant of hexadecimal 10. So CD10, this is pretty much all about it. Great. And then we need to, so what we can actually already run it and we'll see an empty screen, but there still would be a blinking cursor. So in order to get rid of the blinking cursor, we need to perform a few more operations. So we need to set the CH register to hexadecimal 20 and AH to hexadecimal 1, and then call the interrupt 10 hexadecimal. So let's go for it as well. So I have moved to CH. I want to move the constant of 0x20, and just the same thing. So B, W, now the CH register is value for CH is 010. This is the binary value, okay? And then the value to put there is 20, right? So this is gonna be 20. just the constant value to put into the CH register. Okay, and then want to say move to AH. I want to move 0x01 to move 1 there. Okay, so the same thing, BW, and now the register AH, we have 1, 0, 0, and the value, the data is 0, 1, and eventually I want to say call the interrupt hexadecimal 10, and this turns into CD10 just like in the previous part. Okay, so now let's perform the actual assembling. So I would approach this line by line. The reason why I'm doing this like this is because the table with opcode scrolls up, so I won't be seeing this, and I just want first I wanted to get all the information from the table. So now when it scrolls up, I no longer need it. So now I can just make hand assembling, and then we just extract the opcodes into the single line to see them when we turn on the editor, because it all scrolls up. Okay, so it's a bit weird, but you'll get used to it. So I'll just explain it once, and then I hope it's going to be self-explanatory after. Okay, so let's first assemble this line and 0, 3, 0, 0. So B is hexadecimals, then W is gonna be it's gonna be 1, because AX is 16-bit register, so it would be 0 for 8-bit registers, and W is gonna be 1 for 16-bit registers. So 1, 0, 0, 0. Okay, and then the hexadecimal 0300. So let's turn this all to hexadecimal. So this would be B. 1000 is 8 in hexadecimal. If you're not aware of how to convert binary to hexadecimal, you can reference my series on hand assembling. I'm explaining it there. Okay, so B8 0300, and we have our very first opcode, like our very first instruction being assembled, being hand assembled. Now let's move further on. So CD10 is already assembled, so this is going to be just CD10. Then BW 101 and 20 turns into, so this is the register CH, which is the 8 bits. So W is going to be equal to 0. So B, then 0, and 101 and 20. And now let's convert this to hexadecimal. So B 0101 is going to be 520. Okay, so B 520. We got the third instruction being encoded, and then B W 10001 turns into B. Now W is going to be 0 because AH is 8-bit register. 100 and 01 hexadecimal, so this turns into B4. 011 is 4, okay, and 01, all right, and CD10, just to fire this interrupt, just it remains the same. So now we have 1, 2, 3, 4, 5 instructions, and now let's just put these instructions in one line. So I can say B803, and I need to be very precise because the only single mistake would prevent this program from working, so you really need to be precise. B80300, okay, then CD10, okay, then B520, okay, then B401, okay, and finally CD10, okay. So here we go, and now we can go to the editor, all right, and I want to write this at the address 0500s, okay, so the very first, so this is the actual place in memory that the instruction pointer will get there as soon as I type run. Okay, so whatever we have there would be executed. So just to give you an idea. So I need to, and by the way, be careful with the editor because all the apps in GameOS fit 512 bytes, no more. Hence, I didn't have enough space to implement the backspace functionality. So if you type something wrong, you just better restart this app from scratch. So in editor, you don't have a backspace, so beware of that. Okay, so 0500, and now I need to, so this is the address. Now the DI pointer points to this address, and whatever we type after would get stored into memory, right? And we can use spaces here, so we don't have a backspace, but we can separate the bytes however we want. So we can use spaces, but anyway, they would be written like one by one without spaces, obviously. So now we need to type these instructions one by one. So B80300 CD10, okay, B520, okay, B401, okay, and CD10, and hit enter to end the output. So now we have this, there now hit escape to just escape from the editor, and now I want to save this as the prog1. All right. Now I'm gonna run this code, and if I did everything properly, it should result in a black screen, nothing there, and no blinking cursor. So if we do obtain that sort of a thing, that means that we did everything properly. Then we'll reboot, and we're gonna be done. We're done with the first chunk of code, and then we'll go for the second chunk of code. Okay, so yeah, just saved. So let's hit run, and this is it. Black screen, no cursor, which is exactly the output that we expected. Okay. Now when we restarted the operating system, if we go to edit, there is nothing there, right? So we need to load our work from prog1, and if I go back to editor, now we see that the bytes that were written are already there. So the next chunk of code would be written at the address 050B, which is the next byte after the very last CD10. Okay, so let's handle the second chunk and input that chunk in, and then save and run again and see what happens. Okay, so I'm going back to the tables, and I want to have a look at the opcodes. So the next thing that we need to do, so in this app, in this screensaver, we're going to be writing bytes directly into the video memory, and this is absolutely essential. So we're not going to be relying on BIOS interrupts to draw, because it takes less bytes to implement, and it's just I don't know, I just love writing directly to video memory. Probably that's the main reason. Okay, so the video memory, so in order to right there, we need to make some setup first. So we need to initialize the segment being responsible for the video memory, and that's the segment B800, okay? And we need to point ES register, which is the extra segment register, to that segment. And then we'll need to set up the byte in AX. Store the word in AX. So the first byte is going to be responsible for background and foreground color of the character that was supposed to be printed to screen, and the second byte would be the character itself. All right. So then we'll need to reset the DI register in order to later on type a character to a screen using the single instruction store single word. Okay, and as soon as DI would be pointing would be equal to 0, so store single word would be printing to where ES DI is pointing to, and that's the reason why we just why we need to initialize the ES. Okay, and it would be printing there whatever we have in AX. So because store single word still stores a word, right? All right, so this is just a planning, a bit of a theory of how this works in assembly, and now let's put this into code. So first we need to say move to BX. I want to move, yeah, by the way, here you have the backspace, unlikely the editor. So here it's just like a text editor, like a bit of it, like something that looks like a text editor, not real one, but still. 0xB800. So this is the first instruction to encode, and let's go for it. So the same thing, so move instant immediate value, immediate data to register. So formula is B, W stands for byte. So I've been explaining this, so no more things like that, just want to make it a bit faster. So BX, so code for BX is 011, all right, and then the value, so B800, but in little endian this would be 00B8, all right. And let's go further on. Now we need to say move to ES. We want to move the value of BX, and that's how we initialize the extra segment. So now this is another scenario. So you just have a look at the line number 8 or 9, line number 8, I believe. Yeah, line number 8. We put the register to the segment. So the ordering in the assembly and in the table and in the machine codes are different. So just to bear that in mind, because in assembly we have the destination argument first, then the source one, but in machine codes we always have the source one first and then the destination. But in case of the segment registers, we always have the segment first and then the register, no matter whether we put register to segment or vice versa. That's I don't know why that is so, but that's just how it works. Okay, so so the code, the opcode to do this is, so I just look up, so this is 8E, all right, and then the line number 8, so 11 segment and register. So this is a general formula. So what is 11? 11 is the mode. It tells us that we're we're performing the register to register operation. So otherwise, if this would be like 00, it means like register to memory, for instance. All right. And then we need to input the segment register and the register itself. So the segment register is ES, so the code for ES is 000, and the code for BX is 011. Okay, and I think this is kind of it. Okay, right, and the next thing to consider, we want to initially initialize the value of AX. So I say move to AX, and I want to move the constant of 0 to F. Now, what this constant is all about, so let me explain. So the first byte is 02. This means, so the first nibble, the 0, so the leftmost nibble, tells the color of the background, and 0 stands for black, while the 2 stands for the foreground color of the character that we're going to be put into the screen, print into the screen, and 2 is the code for green. So let's say 1 is code for blue, 4 is code for red, I believe, right? And so on. So there is a list of the colors in the GameOS if you just type the theme command, and that allows you to change the color scheme, and you can reference the colors there as well. Okay, so now we need to move this constant. So this would allow the single opcode, store single word, to put this value to wherever DI is pointing to, ES DI is pointing to. Okay, so again the same thing. So B, W, and then the so yeah, the register is AX, which is 000, and then the value. So assuming the little endian order, this would be 2F02. Okay, 2F02. Great. And the next thing we want to, so we could have say move to DI, move 0, but it's a bit shorter way of doing this is just to say XOR DI with itself. So XOR DI with DI. So we have the XOR operation and two registers. Well, actually, this is the same register. Okay, so this is the line number 3, the scenario when we have the register to register operations, no matter whether this the move, compare, and sub, or in our case XOR. So I input this code. It's not 30W as you might have think. It's actually 3 hexadecimal. Then a single digit represents actually 3. Well, let me just put this in. Let me just put this in, and then I'll talk through this because this is a little bit new thing. So I've reinvented the wheel, and this encoding is just how I see things. It works. It results in real machine codes, but I had very little space for putting this opcodes into the single screen basically, so I need to invent my own encoding. So I'm going to tell you how this works a bit later on. Okay, so 3 hexadecimal 0W, and then the mode is 11 because this is the register to register operation, and then we need DI to put it twice. So DI has the code 111 and 111. Okay, so this is pretty much all about it. And yeah, the next thing, starting from the next command, we'll already start the loop that we're going to be referencing in future, right? So starting from the next line, we already get into the logic of actually kind of like doing the loop, basically printing these characters in the loop. So I could have do this in the next chunk, but if I do so, we'll see nothing at the output, because what we've done so far doesn't do anything, doesn't print anything. So I just type 2 more instructions to get a single character being printed on the screen, so just to have a little bit different output to make sure that we did make everything properly, okay? And then we'll complete the final chunk, the rest of the loop, the jumps, and that's the way to go. Okay, so just to bear in mind that starting from here, we are within the loop territory, so every time, every loop, we need to increment the AL. So AX holds the 16-bit AX register holds both the color, the attribute, like a background color and the foreground color of the character, and the character itself. So we want to increment the character. Yeah, and by the way, the 2F, the AL that we have like a couple lines above, 2F stands for a slash symbol, and the next symbol after slash, the ASCII character for a slash symbol, and the next character after slash is gonna be 0. So this inc AL makes the value at AX from 2F to the next value, which is 30 in hexadecimal, so 0 to 30 would be in AX after this. And this would make AX containing green 0, and when we then call the store single word, it would print the green 0 to whatever DI is pointing to, and DI is currently pointing to 0, to the very first element. So in the top left corner, the leftmost cell would be containing a green 0. So I hope this is clear how it works. We'll see this in the output, obviously. So now we need to increment the AL register. Okay, and yeah, in order to do this, we have a special opcode. So this is FEC. You can see this on the right part of the screen still. So for 16-bit registers like AX, increment AX, we have the lookup opcodes like 40, increment BX, lookup opcode 43, CX 41, and so on. But for 8-bit registers, the encoding is a little bit different. So we have FEC, and then we have 0, and then the register. So in this case, the register is AL, and the value for AL is 000. So this is going to be 000. This is it. Okay, so now the chunk is no, sorry guys. So one last thing, the most important, store single word. So here I use the lookup. So the code for the opcode for store single word is AB. Okay, and now let's go for hand assembling. So starting from the first line, so BW011 00B8. Yeah, and this turns into B. So W is gonna be so BX is 16 bits, so 1 0 1 1 0 0 B8, and this turns into B, and 1 0 1 1 is B in hexadecimal, 0 0 B8. Okay, let's go further on. So 8E. And now I just need to change the layout so we have 4 digits in a chunk. So this would be 11000011, right? And this is gonna be 8E, and 1100 is C, and 0011 is 3. Okay, so 8EC3, which is correct. Okay. Now the next one. So B, so BW 000 turns into, so AX is 16-bit register, hence this would be B1, so W turns into 1, 000 to F02, and this turns into B8 to F02. Okay, BA to F02, which is correct. Okay, the next thing to XOR the DI. Okay, so, or no, hold on a second. Yeah, XORing the DI. Yeah, so this one is interesting. So what this means, I'll now try to explain. So how to decode this sort of a thing. So if W is not through the space but just goes directly, so the first digit is hexadecimal. Okay, then we have 0 and W like this. So now it might not always be 0, it might be, say, 4 or 3. So let's say if this is 4, we need to convert 4 to binary, and in binary 4 is going to be like this, 5 is going to be like this, this is going to be 6, this is going to be 7, and this is going to be 0, right? And I'm using only 3 bits here to represent, because the 4th bit is actually the W, all right? And now the W stands for whether this is the 16-bit register or 8-bit register. So we're dealing with a DI, which is 16-bit register, so this is gonna be 1, okay? And yeah, and then, so we just put the layout, make the layout so we have 4 digits in a chunk, and this eventually turns into 3, 1, F, F, and that's the way to go. So this is the instruction. This is the XOR DI with DI, which resets DI. So 3, 1, F, F. This is pretty much all about it. Okay, and now the INC AL. So we have FEC000, which turns into FEC0. So this one is pretty simple. And then we have the AB, and it's already hexadecimal, so AB. All right, guys, now we need to type all the instructions one after another and then input them as the second chunk to our hex editor. So let's start from scratch, and we're going to be very careful. So BB00B8, okay, then 8EC3, okay, then B8 to F02, B8 to F02, okay, then 3, 1, FF, all right, 3, 1, FF, okay, then FEC0, FEC0, and finally AB. And this AB star single word, it should bring the green 0 to where the eyes point into, which currently is going to be the top leftmost character. So call number 1, row number 1, so there in the top left part of the screen. Okay, and now let's go to the editor. Okay, and now we need to, as I've been mentioning before, we need to calculate the proper offset to keep inputting the byte. So if we say 0500, we just override what we have. So we need to skip the number of bytes taken by the instruction. So I've already calculated that value, and this is going to be 050B. And now I just need to input all the opcodes, all the instructions. So BB00B8, 8E, C3, okay, B8, 2F02, all right, 31, FF, okay, FEC0, and finally AB, and hit enter. So we have these instructions as well. Now we'll save this as prog1 and try to run, and if I didn't make any mistakes, it should print a green 0 at the top left corner of the screen. So let's have a look. So I escape from here, I say save as the prog1, okay, and I hold my breath and type run, and we have a green 0 in the top left part of the screen. Can you believe this, guys? Okay, so the next step and the very last thing to consider is the most complicated one, by the way. We need to finish the loop. So what we've been doing so far, so we just print a single character, but we also need to increment this character, so it goes like 0, 1, 2, 3, 4, 5, 6, 7, 8, and up to 9, all right? And then also we need to add 2 to DI in order to print them, not like every next column, but to skip one column. So that's the logic, okay? So now let's reboot the system. Okay, so now let's load prog1. Okay, go into the editor, make sure that the bytes that we've entered so far are already there, and they are. This is great. So let's go back to tables and complete the very last chunk, okay, which hopefully results in making this matrix screensaver. Okay, so now two most essential things we need to do. Well, actually, one last essential thing to do is to increment the DI twice to type this digits, not in every column, but skipping one column. It just gives this matrix-like effect, which is cool, right? So we need to simply say add to DI. Okay, and then when it comes to jumps, we're gonna be relying on the number of bytes we need to jump to the certain instruction, but I just put that onto the paper just to avoid this video lasting forever. But I will talk through how to encode those bytes properly. So anyway, let's start with saying simply add. So to DI, I want to add 2, right? And here is the special case. So unlikely the casual add-in, here we don't use the opcode 80 or 81, but instead here we have a special case, and I did put this into the table. So line number 3 in the instruction format, so add 83 for SI and DI. So we have the special code of 83 here, right? And yeah, and then all pretty the same as just moving the I'm sorry, not I said like a register to register. No, it's like immediate data to register. So it doesn't work like for all the rest of for adds. Like it also has 8 or 80 or 81, as you can see in the line 1. But for DI and EI, we have the special opcode. All right. So then the formatting. So we have mode 11. Then the question mark. So we need to go to the question mark table and there find the operation we need, and we need the operation of adding. So this is going to be 0, 0, 0, all right? And then the register. So DI is 1, 1, 1. And then the value is 0, 2, right? Okay, so I hope this is correct. Yeah, it should be. So let's go for the next instruction. So Now we need to answer the simple question whether the cell on the screen or where the eye is pointing to has already exhausted, like has already went off the screen borders or not. And I've pre-calculated this constant, so we have 80 multiplied by 25, and then we need to multiply this by 2 because we have a word, not a byte, but a word per cell on a screen, because the 1 byte for attribute, another byte for character. Okay, and then we need to turn all of that into the hexadecimal, and that would be the constant of 0xFA0. So I've used just the hex calculator to do this. This is the part of my preparation for this video. Okay, so anyway, we need to say compare, and comparing di with this constant value of 0x0fa0. So literally asking, like, did the eye went off the screen or not? And if it did went off the screen, then we want to jump to the line that resets di back to 0, the line of XOR di to di, and that would take exactly 12 bytes. But that's going to be the story of the next line already, right? The next line, or is it? Yeah, the story of the next line. All right, so let's encode this one. So we have compare register and comparing the register and the immediate data. So here, so 80W, and then the first line in the formatting, so 11, instead of the question mark for compare we have 111, and then and then for the register we have di, which is 111. All right, and then the value would be A0 0F because of the little Indian byte order, so 800F. Okay, yeah, this should be just fine, right? Okay, so the next thing, if it is equal, so jump equals, so if the I is really equal to this, or the constant of hexadecimal 0FA0, in this case we want to jump back to the line where we were resetting di by saying x or di, or in hexadecimal or in machine codes this was 31FF instruction. So you currently can't see this, but I have this I did put this on a paper and just put some notes. So the next thing we need to do, we need to calculate the number of bytes from before this instructions, like this jump equals, and up to the one where we have the x or di to di, or 31FF, including that one, and that takes exactly 12 bytes. So if I just start showing you this, I'll lose the work that I've done so far. I don't really want to do that. So that's just the matter. So we need just to calculate the 8-bit offset. So like how many bytes from before this current jump equals instruction up to the one we want to jump to, including the one we want to jump to, right? And that takes exactly 12 bytes, or in hexadecimal that is gonna be C. But this kind of like offset, we can say like just C. This is how many bytes. This means how many bytes. Like, well, actually, I just say jump equals print, and here I just say that print actually takes 12 bytes, and in hexadecimal it would be 0C, right, like this. Okay, and now let's convert this as well. So jump equals is the part of conditional jump. So in the right part of the screen you see JCC and cons in the parentheses. So this is the conditional jump. So we have 0111 plus TTTN is the type of jump. So we go to the TTN table, the upper part of the screen, slightly to the left. So key and TTTN. So jump equals, the very first line is 0, 1, 0, 1, 0, 0. Okay. So this is the code. So this is gonna be 74, right? And then the number of bytes. And now here, I just say 0C for now, but the way to encode this, bear in mind the fact that we're jumping backwards, not the forwards. We need to make some extra operations as opposed to if we're jumping forwards. So here, I just say that we're going backwards, just not to forget this. Okay, great. So the next thing, we might run out of digits for ASCII characters in the AL registers. So if we hit the character of colon, we need to go to the reset part that we didn't yet implement, but we're gonna implement this in this chunk. That would be setting AX register value back to its initial 0 to F. All right, so it's really easier to do rather than to explain. So let's go. So we need to say compare, and I want to compare AL with 0x3a. And again, like bear in mind that we're comparing AL. AL contains the character. AH contains the attribute, like green foreground, black background. And 3A stands for is the hexadecimal code for ASCII colon, I believe, or 9. Yeah, probably it's colon. I just have that value precoded. Okay, so let's turn this into the machine codes as well. So we have compare a register with the value scenario. Okay, so this is gonna be 80. No, so sorry, hold on a sec. Yeah, sorry guys, just I thought to use the general compare opcode, but for AX, for compare, add, sub, and or an XOR, we have the specific code. So for AX it would be 3D, but this D might be observed as 000W, where W stands for a bit, like 1 for 16-bit, 0 for 0 for not like this. Actually, to make it D, it's gonna be 1101. Yeah, like this. W stands for, would be 1 for 16-bit registers and 0 for 8-bit registers. So AL is an 8-bit register, so it would be like this. So, and in hexadecimal, this is going to be C. So this is just a lookup. We just don't have this in the table explicitly, but this is implicitly clear from this AX3D in the compare column in the line number 6 and 7. So the opcode 3C, and then the value to compare with is 3A. So this is the very handy and short way of how we can deal with this comparison when it comes to AX register or AL register in particular. So this is how it works. Okay, so and in the case if AL actually equals to the 0x3a, so it equals to colon, we need to reset AL back to 0. Okay, well actually back to slash, because we're going to be jumping then we're going to be jumping to the start of the print routine. So, and by adding 1 it would be like again like 0, 1, 2, 3, 4, etc. So here we want to say jump greater or equals in this case. Yeah, so we used jump equals before, right? So did we? Hold on a sec. Yeah, 70, 74. Yeah, which was jump equals. Yeah, and now we need to use jump greater or equals. We could have used jump equals as well, but jump greater or equals just results in a little bit more prettier output eventually. So I'm using the jump greater equals here. So jump greater equals to, and if this was a label, I could have say reset reset AL or reset AX actually. Yeah, but like in machine codes, we don't have labels, we don't have variables like we have them in assembly. It's all the matter of the either absolute or relative addresses. So we need to skip 2 bytes forwards. So I just already know this because I have all the code is written on the piece of paper. Okay, so we just need to skip 2 bytes here. Yeah, so let's encode the jump greater equals and then just precode 2 bytes and say that this is going forwards. So conditional jump is 0, 1, 1, 1, then TTTN for jump greater equals is 1, 1, 0, 1, which is D, right? And we have 2 bytes, we have 2 bytes like this, okay, and forwards goes forwards. All right, so this is it. All right, 2 bytes goes forwards. Okay, and now after, so here we are coming to the end of the loop printing. We are at the end of the loop basically. So now we need to jump to the next iteration. Like we're gonna have kind of 2 loops. So the one that resets DI and kind of prints everything from scratch, and the second one only resets the AL. So here we would say like jump to the next jump to the next byte, let's say, right? But what the next byte is? The next byte is where we do increment AL again. So I hope that's clear. And this is unconditional jump, and it takes all exactly 16 bytes. Yeah, or in decimal or in hexadecimal is going to be 10. So we need to use this conditional jump, and the conditional jump is E, right? 1 0, no, sorry, E followed by 1 0 1 1, which is B, right? Yeah, which is B, but let's keep it like this for now. And then the number of bytes, so it's 16 bytes or it's 10 hexadecimal, so 10 hexadecimal, and we're going backwards. So this is important because the encoding for going backwards is different from encoding for forwards. So if we go forwards, we just have this constant of bytes to jump over, and if it goes backwards, we need to use some tricks, which I'll cover just right in a moment. Okay, so and now you remember just we've jumped 2 instructions forward to reset the AX, and now we can assume that this is currently the next line. The line we're going to be now typing is the line to reset the AX. So I just simply say move to AX, and I move back the constant of 0 2, so green character on a black background, and 2F, right? Yeah, so let's encode this one. So B W AX is 0 0 0, right? It's not already seen, unfortunately, so this is a little bit of a downside, but yeah, let me just yeah, 0 0 0 for AX, and W is going to be 1, yeah, and respectively 2F 0 2 in the little endian byte order. Okay, 2F 0 2, all right, and yeah, this is it. And eventually the very last thing, so after we did reset this AL, we need to jump back to the next byte. Okay, so jump back to the next byte. It's a conditional jump, so again, like jump to the next byte. Okay, and in this case it's the well, I have actually pre-calculated that, so it's gonna be 21 bytes, but in hexadecimal it's gonna be 15. So again, like the same thing, so E B, and 15H, and this goes backwards. All right. Okay, great. So now let's do this hand assembling and then input our last chunk, hopefully to see how we enter the matrix. Okay, so let's start from this one. So 8, 3, 1, 1. Now I group by 4. Oh, okay. Let me just do this in the next run. So 1, 1, 1, 0, 2. So this is gonna be 8, 3, 1, 1, 0, 0, 0, 1, 1, 1, 0, 2. So this is gonna be 8, 3, C, 7. All right, 8, 3, C, 7, and the constant of 0, 2. Okay, F 8, 3, C, 7, 0, 2, which is correct. The next one, so 8, now 0W, so this is gonna be like this, and W is gonna be, so we have DI, which is 16 bits, so this is gonna be 1. Okay, then 1, 1, 1, 1, 1, 1, 1, 1, A, 0, 0, F turns into 8, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, A, 0, 0, F, which turns into 8, 1, F, F, 8, A, 0, 0, F, 8, 1, F, F, A, 0, 0, F, which is correct. Yeah, right? Okay. So the next one is jump equals to print, right? So 0, 1, 1, 1, 0, 1, 0, 0. And yeah, and here we go in backwards, 0C. So first, let's turn this to binary. This is important. So I turn 0C into binary. So this is going to be 0, 0, 0, 0. And C is 1, 1, 0, 0. So pay attention, guys. So here is very important. It's very important here. So we can already convert the left part. So this would be 74, right? And now so when we go in backwards, we need to do two things. First, we need to invert the bits. So all the zeros in the relative 8-bit offset would turn to ones, and then we need to subtract 1 from the last 4-bit chunk. So this is gonna be like 1, 1, 1, 1, then 0, 0, 1, 1. And now minus 1 from this. Okay, minus 1. So this is gonna be like this, 0. And eventually we have 7, 4, 7, 4, F2, right? 7, 4, F2. Yeah, this is what we need. Okay. The next one is 3C, 3A, which is 3C, 3A. We already got this, so 3C, 3A. Okay. And another, so the next is jump forward, so 0, 1, 1, 1, 1, 1, 0, 1, 0, 2. So this is gonna be 7, 1, 1, so 7D, right? Yeah, 7D, 7D, and 0, 2. So here we do nothing to 0, 2 because we jump in 2 bytes forward, so nothing to be done there. So just 0, 2, nothing special. Okay. So now the jump again, like jump backwards to the next byte when the print loop is over. So we have E 1, 0, 1, 1. This is B probably, yeah, 10H, and we go backwards. 10H. So 0, 0, 0, 1, 0, 0, 0, 0. So this is 10H in binary. Okay. So this is gonna be EB, right? Yes, EB. And now invert the bits. So 1 1 1 0 1 1 1 1, and minus 1, it's gonna be 0, so eventually turns into E B E E. Okay, great. The next one is B W for AX, so this is going to be 1 0 0 0 because AX is 16-bit. 2F02, so we've been encoding this already, right? So this is going to be B8 2F02, B8 2F02, great. And last but not least is the jump to the next byte from after resetting the AX register. So E1011, and now I need to convert 15 hexadecimal to binary, so this is going to be 0001, and 5 to hexadecimal 0101, right? So this is going to be EB. Let's go like EB. Now inverting the bits, so 1110, 1010 minus 1, so 10, and this is going to be 9. 9 is going to be like this. So this is 10, so minus 1, this is going to be 9, and this is 9 in binary. So this turns into E9. Yeah, and this is pretty much it. So, oh my god, guys, now we need to complete the very last chunk, and hopefully this would result in something interesting. So, let's go. So we need to be very precise. So 83C7. I just type this opcodes, this instructions in one row now. C702, 83C702. Okay, then 81FFA00F, F1FFA00F. All right. 74F2, 74F2. 3C3A, yeah, 7D02, all right, EBEE, right, EBEE, now B8 2F02, B8 2F02, B8 2F02, and finally EBE9. Okay, so yeah, I really hope this is the case. So oh my god, now hold my breath, guys, and let's go to the editor, and we need to type this bytes next. And I already have the offset, so this is going to be 0518, and now we need to type all of these bytes in. So very careful. 83C702. Okay, 83C702. I just double check with my notes because otherwise it's just not going to be working. Okay, then 81FF 81FF A00F, 81FF A00F, okay, 74F2, 74F2, okay, 3C3A, all right, 7D02, 7D02, all right, now EBEE, EBEE, okay, now B8 to F02, B8 to F02, and finally EBE9, so EBE9. Oh my god, guys, and is this just want to double check? So yeah, seems like this is it. So hit enter. Now I want to save this as prog1, and now the moment of truth, guys, is if I did input everything properly, when I now type run, we should enter the matrix. So are you ready for this? Run. And here we go! Can you believe this? Can you believe this? We just created a matrix screensaver in x86 machine codes. I don't know, guys, like, I'm so excited about this because in order to prepare for this video, I've been doing this, what I've been showing you this within this video several times in the row, and it wasn't really trivial to type everything properly because I was missing the where to input the bytes, or the bytes were missing, or I just made some mistakes in hand assembling, and that wasn't really that great. But now, like, when you do this from the very first take, it's really amazing, and this is such a great feeling. You really feel like you're in the matrix, basically, like, not as a slave, but obviously as you control it as an architect, right? So this is so cool. Okay, so the very last thing I want to demonstrate is how this works on a real hardware. It just looks really cool, almost like in the Matrix movie, in the intro. They are like not in this teaser trailer that we currently see on YouTube, but those happened like 18 years ago. So let's have a look how this looks like on the real hardware, and then that would be pretty it. So yeah, I just say goodbye to you guys. So I hope you learned something interesting out of this tutorial. Thanks for watching. Again, like, bear in mind that you can follow the steps being represented in this tutorial using the GameOS image that you can download from my GitHub. The links would be in the description below the video. So it's a really challenging thing to try at home, so I encourage you to do so. This is gonna be unbelievable experience and unforgettable experience completely. Well, okay, guys, yeah, this is it from my side. So thanks for watching. Until the next time, and take care.